Assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
This problem concerns an alpha decay of a uranium-238 atom into an alpha particle, if you'll remember, is a helium nucleus that has atomic mass number 4 and atomic number 2, as well as the remaining daughter nucleus. In this problem, you're asked to find the recoil kinetic energy of the daughter nucleus, as well as the Q value of the entire decay process. I've looked up the atomic masses of uranium-238 and an alpha particle, but it actually turns out that in this problem, you don't need them. So the important thing to remember, though, is the important conservation property in physics, conservation of momentum. Here we show, I've illustrated it as the alpha particle, showing a much smaller particle in green going one direction with a faster speed, a faster velocity in this case, and then another daughter nucleus of the decay, which is much larger in mass, so I have a bigger circle here, and that has an equal momentum going the other direction. Because momentum is conserved, this higher mass particle will be moving at a slower speed in the opposite direction. This conservation of momentum can be mathematically expressed as follows. The mass of the alpha particle times the velocity of the alpha particle, and that's a vector, equals the negative product of the mass of the daughter nucleus as well times its velocity. And with this relationship and noting that the direction of the daughter nucleus is exactly opposite that of the alpha particle, we can express this in terms of scalars. The speed of the daughter nucleus is, though it turns out, can be expressed as the ratio of the speed of the alpha particle, and that ratio specifically is the mass of the alpha particle over the mass of the daughter nucleus. Mind you, we still don't know what this is, this daughter nucleus, so we're just substituting in D for daughter here. And it turns out that we don't really need to know the specifics to solve for that. The kinetic energy of the alpha particle is the standard 1/2 times m times the speed squared. The kinetic energy of the daughter nucleus we express the same way, but we are given the kinetic energy of the alpha particle here. So we can solve for the kinetic energy of the daughter nucleus in terms of the kinetic energy of the alpha particle. And if you substitute in our relationship derived from conservation of momentum into the kinetic energy of the daughter nucleus, you can regroup the terms and see that the kinetic energy of the daughter nucleus is a ratio of the kinetic is proportional by a ratio to the kinetic energy of the alpha particle, and that ratio is the mass of the alpha particle over the mass of the daughter nucleus. We know also from our decay equation above that if a uranium-238 atom undergoes an alpha decay, whatever daughter atom is left over will have an atomic mass number of 234, or at least temporarily, because that atomic mass number has to be conserved in this equation. So we know roughly that the mass of the alpha particle is around 4, and we know roughly that the mass of the daughter nucleus is around 234. And since these are so they differ by 2 orders of magnitudes, we're not going to concern ourselves with the decimal points. It's going to be a small number, and the decimal points of the precise atomic masses aren't going to contribute to much. So we are going to sub in these 2 values for our ratio in this expression here, and multiply that by the kinetic energy, which is of the alpha particle, which is a given in this problem. And lo and behold, we end up with 0.0718 mega electron volts for the recoil energy, kinetic energy of the daughter nucleus. From there, we can find disintegration energy of decay, or the Q value, that is another name for it. And that is just the sum of the kinetic energies of the decay products of the decay. And we have the kinetic energy of the alpha particle, that's a given. And we just calculated the kinetic energy of the daughter nucleus. All we have to do is add those together, 4.20 mega electron volts plus 0.0718 mega electron volts. And that leaves us with a Q value of 4.27 mega electron volts. That concludes our problem.